Our next topic and last topic is MPLS. MPLS stands for Multi-Protocol Label Switching. It belongs to a family of data packet network technology that is very different from everything we have seen in TCP-IP and in particular in IP. It is what we can call the connection-oriented network layer. This is a technology for networking that predates the internet, predates IP, and is based on a very different paradigm. It is used today, but it's not very visible to end users. It is essentially a backbone technology. It is used in the backbone of internet service providers. And it's also used in industrial automation networks like smart grids. This is why we talk about it. So about the principle. What is connection-oriented network? The network for us is IP, or also the MAC layer. Both of those networking layers are connectionless. Connectionless, roughly speaking, means we use the paradigm of the post office. When you send a packet, the main thing that you need for the packet to reach the destination is a destination address. At the IP layer, it is the IP address, of course. The connection-oriented network layer uses a very different principle that is more inspired by the telephone network. This drawing is illustrating how things happen. We have here S1, S2, S3, S4 that are intermediate systems of this connection-oriented network layer. They are called MPLS routers. Sometimes they are called MPLS switches. And you have hosts also here. Although in reality, it's very rare that an application or a device uses MPLS directly, but I'm using this as an illustrating example. The difference between IP and connection-oriented layer is how the tables in the intermediate systems are organized. Let's look at one entry of a table. One entry of a table here is one column. For example, this column means anything that arrives on input number 3, on interface number 3, that comes in with a label number 1. Label is a value that's in the packet header. Will go out to output interface number 2 with another label, which in this case is the same here. So packet headers contain labels. Labels are numbers that are not addresses. They're just numbers that are used to differentiate between different flows on a given link. So here we have the green flow of data. When A sends a packet to C using this mechanism, it has to put in the header of the packet, if it uses a connection-oriented layer, a connection-oriented mechanism like MPLS, it will put a label number 2. There is no concept of a source label or a destination label. A label is just a label. So it will put number 2. S1 will receive this packet. It knows it comes on interface number 3. It'll go into the table. It will do a match and find number 3 in and label number 2. So it will be the second entry in the table here. And the table instructs S1 to send the packet on output number 2 with label number 2. So the label is typically changed. Here the value happens to be the same, but the value of the outgoing label is the one given by the table, not the one given by A. So the packet will arrive at S2 on interface number 1 with label 2. S2 will do the same thing. It will go to the table. It will find this column. The column says go to output number 3 and change the label to 1. So this packet will now have a label of 1. At S4, something similar will happen and the packet will be delivered to C. The red flow instead, when it reaches 1, has a label 1. So the labels have to be different here. Otherwise, there's no way to distinguish the flow. So the red and the green must have different labels. When they go out, they must also have different labels because they go out on the same physical link here. However, at switch S2, the red flow goes to output 4. Therefore, there is no need to differentiate the label. Label 1 here, we see, is the same value as here. Doesn't mean they are the same flow. It just means since they are not on the same interface, their labels cannot be compared. So this is the principle. What is a major difference with IP is that we do an exact match in the table here. We need to find exactly one correspondence for the input and the label. If S1 would receive a packet from A with label equal to something else than 1 or 2 here, this packet would simply be dropped. Of course, this works only if all the switches have the correct values of the tables. Now, there's a big difference with IP. Those values of tables are related to flows. So before all of this to happen, before A can talk to C using this mechanism, we need to have a preparation phase, which is called the signaling phase, where A first talks to the intelligence of the network, or a network controller somewhere instructs all the switches of the values of the label. This is called signaling because this is similar to what happens in a telephone network. If A wants to talk to B over the telephone in the old days of circuit switching telephones, then you needed to call someone by dialing the numbers, and the calling caused the circuits to be switched in all the boxes. So that's the analogy. That's where it comes from. It existed in a number of varieties. Today, the only technology that uses this principle is called MPLS. We will see in an example why this is interesting. But before, let's look at how it happens. An MPLS packet is simply an Ethernet packet that has an MPLS header instead of an IP header. A normal Ethernet packet is an IP packet. IPv6 would be the normal case today. So this is indicated by the ether type in the MAC header, as we remember. There is an ether type for MPLS. In fact, there are multiple ether types for MPLS. There is one for MPLS unicast and another one for multicast. We will discuss only about MPLS unicast. So when the Ethernet header says this is MPLS, then the next header is the MPLS header, which is the label. It is essentially the label that I've illustrated before. Labels can be stacked. There can be multiple labels. We will explain why in a second. Therefore, you need to explain, to say whether this is the last label or not by having a bit that indicates whether the next header is a label or something else. Something else is typically an IP packet, but we will see it can be also an Ethernet packet. We will see an example of why this is used. There's also a TTL for the same reason as there is a TTL in IP. In principle, there should never be loops, but if by accident there is a loop, the TTL will take care of killing the packet here, if there is a loop between MPLS devices here. There's also a quality of service indication, which we will not discuss, but you can easily imagine when we've done the network calculus part, this can be used by the MPLS switches to map the flow to one of the priority classes, for example. Here is the example that explains practically everything you need to know about MPLS. So this is showing a system that has MPLS switches that are in fact routers. Today it is typically the same machine that works both as an IP router and as an MPLS switch. When it receives a packet, if the packet through the ether type says it is an MPLS packet, then it uses its MPLS function to do something with it. If it's an IP packet, then it will do the usual stuff we've seen with IP. The main difference, of course, is that all the MPLS stuff requires setting up the MPLS flows, what are called, in fact, MPLS connections. We've discussed that. So here I assume all those tables have been set up by some mechanism that we will not discuss in detail. This can be done very typically by SDN or by other mechanisms that we will not discuss. Here I'm showing 3 MPLS connections, a green, a blue, and a red one here. And I'm showing also the tables, the MPLS parts of the tables at the different routers. In MPLS terminology, there is a distinction between an edge router, LER, it's a label swapping edge router, and a simple label swapping router. So sorry, this is a label edge router and a label swapping router. In IP, we don't do that. Whether a router is at the core of the network with no host connected to it, or whether there are hosts connected to it, is completely irrelevant. MPLS is much more complicated. It's telecom stuff. It's done in a very unnecessarily complicated way, so they make this distinction. But let's look at the tables here. At this box A, which is an MPLS machine, it has this table that I showed a minute ago in a simplified way. Here is how it really looks like. It has, instead of simply a label, it is called a flow spec. Flow spec means, here, since this is a labeling edge router, the incoming thing is not an MPLS packet. So this is a system that connects to the normal parts of the world. I would say what we see in the Internet Engineering workshop, for example, we don't have MPLS. So we just see Ethernet things with IP packets and perhaps virtual LANs. So here the flow spec instructs this edge router what it has to do based on what it sees. This is very similar to what we discussed when we saw SDN. We saw that a modern router today doesn't simply do lookup in its IP table, but it can have what is called flow spec. It can do things on a packet based on more information than simply the destination address. So this is exactly what happens here. Here it says anything that comes on input E, that's the name of an interface, that is an IP packet, and has a destination IP address that belongs to this block, 10.2.2/24. It could be an IPv4, it could be an IPv6. Here it's an IPv4 address. Anything that satisfies this criterion should go out into an MPLS label A, it should go out with an MPLS label 50 on the interface A. So everything that comes here is in fact the green, will go here. Go out on this MPLS label, that means the IP packet is taken unmodified and is encapsulated inside an MPLS packet. So from the viewpoint of IP, from this point on, there is no IP router. So this packet is encapsulated here. When it reaches the end, it has done only one hop, as if there would be exactly one link here. But in reality, there is a network that is typically large. MPLS is used for backbone technologies. At the next hop, this packet has a label 50, so that's business as usual in the connection-oriented network layer. It comes on C with label 50. The table says go out on A with label 34. Here it comes in on C with the same label, 34, and the table says go out on A with label 49. So in B, it will arrive with label 49, and then the reverse of what is shown here happens here too. It says anything that comes in on input A with label 49 should be popped. So pop means remove the MPLS header. So here I said out, the out more precisely should be push an MPLS header. Here you remove one MPLS header, which is called pop. That's the terminology of queues. And then the table says also what kind of packet should be there, because the information has been lost from the MPLS header. If you remember what we saw a minute ago, contains essentially a label. It doesn't say what is the nature of the packet that is contained in it. So this nature was carried in the Ethernet header at this point here. If this packet arrives over Ethernet, we know it's an IPv4 packet. But when we put it inside an MPLS label, behind an MPLS label, we've lost that information. We've not really lost it. The idea is that the label is something very, very well associated. The green label, the green MPLS connection, is associated with some information that is kept by the control plane and is therefore written in this table here. Similarly here, everything that is blue, that is everything that arrives on port D and has this destination address, follows a different path and arrives through a different route to the same node here, where something else will happen, or it will be delivered to another port, but with as an IPv4 packet. As an IPv4 packet, what means what concretely? Well, it means when I will create the MAC layer header, I will put ether type that corresponds to IPv4. If we look at point number 1 here, we see that there are multiple packets that are in fact private addresses, but that can be carried through this backbone. So this is one of the uses of MPLS, is to be able to extend private IP addresses beyond a backbone here. And in fact, the green and the blue can even belong to two different organizations. Perhaps one is Nestle and the other is whatever company, UBS. And this could be Swisscom network, for example, so that there will be no collisions of the different networks that are carried through this infrastructure here. The red flow is something a bit more bizarre, but that happens a lot in the context of industrial networks like smart grid. It's called VLAN interconnection. That's something dirty that should not exist, but exists because of the evolutionary need to make things work without having to go to big changes. What are the things that we want to make work? Assume you have here a set of devices that operate only at the MAC layer. We've discussed last week, we've seen that in an industrial networking context that exists. You have devices and applications, essentially hardware systems, that communicate directly at the MAC layer. If you want to interconnect two parts of substations, for example, or a server that needs to talk to some devices in a substation, and if all those systems are using only MAC layer software, protocols and software, so system that doesn't use IP addresses, for example, the normal thing would be to convert everything to IP and do it like everyone is doing. But another way is to put all the traffic of this local area network inside MPLS label so that it goes to the other end of the world, to a remote center, that therefore will have the impression of belonging to the same local area network. So we can extend one local area network through MPLS to different parts of the world. This is one of the other uses of MPLS. In that case, the MPLS table here will instruct the system here that what is going out is an Ethernet packet, not an IP packet. So whatever was encapsulated has to be put exactly the same way. Perhaps it contains an IP packet, although that would not make a lot of sense, but it's not entirely excluded. MPLS, the way I have presented it, is not scalable. Why is it not scalable? Well, because The routers that are in the backbone, like this one here, router A, need one table entry, like here, one line per connection. So every flow here requires one entry here. So of course you will not have millions of connections in this table. That would be too large. The lookup time would be too large. So what can we do to solve the problem? One thing we could do is avoid having connections and use IP, but another way is to use a hierarchy. That's the classical mechanism. When things become too complex, you put a hierarchy of things. So you can put MPLS connections, which are called LSPs, label switching paths. An LSP means an MPLS connection. You can put connections into connections. For example, assume you are a provider, that's the green part of the network, that gives access to a number of customers that have those blue edge routers. So the blue routers are typically at the customer premises. One is for a company, Nestle. Another one is from a company, UBS, for example. And this is one of your big nodes in Lausanne. And then you need to interconnect to Zurich. Now, Swisscom doesn't have zillions of paths from Lausanne to Zurich, so it has a number of paths. It has a relatively small network. Backbone networks are typically small in number of routers. They're big in the speed of the lines, but they're small in the number of routers. So here it doesn't make sense to have each of the blue MPLS connections that each correspond to one company be seen as individual connections by the rest of the backbone on the way between Lausanne and Zurich. So what you can do is establish one MPLS connection from the MPLS router R, that's the green one, to the MPLS router B here. So that's an internal MPLS connection that would be used only by Swisscom. It has label 50 here, it has label 59 here. Remember, the label is something local on the link. Then this router in its routing table can have something that says anything that is blue that comes with label 10 here, for example, is put inside an MPLS connection, which means that if we do a packet sniffing on the output, we will see two labels. The label 10 is this one here. It is put inside an MPLS connection. That means it is put after a label 50. Then those MPLS routers, when they see label 50, their table says just change label 50 to 34. So they will look only at this label, not the rest. Whatever is here, it will not be visible to this router. In contrast, when the packet comes to LER-B at the edge of the network here, the table will say whatever comes out with label 49 should be removed from the MPLS connection. This is what we call pop. That means we delete one header, the label 49 is removed, and then we look at the next thing. What is the next? Well, label 12. Then we go again into the routing table, into the MPLS table, and we look at what to do with label 12, which may involve simply putting it on an interface or some other actions. So it is similar to recursive table lookup we've seen with IP. Here we do recursive MPLS label processing, and this can be used to simplify the network and have fewer MPLS connections. So typically you construct MPLS connections from one edge of the network to the other edge where you have traffic, and then everything that goes here is put into the system. You typically have two levels, sometimes three, but most of the time you have only two levels. Why do people use MPLS rather than IP? One of the reasons is private addresses, like we've discussed before. Another reason in the context of industrial networks is the ability to have what is called fast reroute. What is the problem? The problem is changes in network topologies and failures. How does an IP network handle this? Well, if a link or a router breaks in the network, what happens? In principle, we have a routing protocol like OSPF or BGP or both that will discover the change. We'll redo a computation. In the case of OSPF, we'll flood new LSAs to all OSPF routers. In the case of BGP, there will be withdrawn of a route, etc. So the routes change will, if they repair the error, the fault, if there is enough redundancy in the network. But this takes time. It takes time because it typically involves a negotiation or a recalculation by multiple routers. And in the case of BGP, the number of changes that are involved may be very large. So a BGP router may take several seconds to process a change. For industrial things like smart grid, remember, if we use smart grid to do information that the sensor has sensed something that goes wrong, and we need to pass the information to another actuator, for example, to change something on the line, this must happen very fast. If we go through MPLS, we will not be able to have reroutes at the timescale of 1, 2, 3, 4 milliseconds, like some smart grid application require, but we will be able to have reroutes at the time with a horizon of 50 milliseconds or less, which means that if there's an error, if there is a fault, if there is a router that crashes, gets destroyed, or a link that's broken, then the path will be changed within 50 milliseconds. How can you do such a fast change? Well, there's no magic. You need to pre-compute an alternative path. So when A sets up an LSP, or what I call an MPLS connection to B, in fact, if this is a mission critical flow, it will set up two. There are multiple ways to set up two. They can be in hot standby or in cold standby. Hot standby means that both are working. Cold standby is that the red one is not yet set up but can be set up very fast. I will assume here they are in hot standby, which means that the two MPLS connections are operational. The tables have been written that allow the packets to be switched. If this is a connection that requires reservation, like we have seen last week, if you want to make sure there is zero packet loss due to congestion and very small delay, and this is probably the case, because if you care about such a high level of redundancy and such a high level of quality of service, you typically will also require to do network calculus on those connections. So you reserve the capacity on the red path and on the green path. Then the traffic is sent typically only on one of the paths, although there's also the possibility to send it on both paths together. We'll talk about it a bit later. But if you send it on one of the paths, then you rely on what is called a fast detection using hello BFD messages. BFD messages is something we have discussed already in the context of OSPF. BFD is a simple protocol that's used between two routers, including two MPLS routers, where two routers send typically every 3-4 milliseconds, they send a message saying, here I am, do you hear me? And you respond, yes, I heard you, here I am too. And A and B monitor, so two routers like this one and this one, monitor each other. So A and P monitor each other. And if they discover that there is something broken, then after typically 3 messages being lost, so after 10 milliseconds, they detect the loss here. So this will be used to detect that the loss, a link is broken here. To detect the loss of the path, all routers along the path do it. There is also another type of BFD messages that is sent by A to B and vice versa. So there are link local BFDs and what is called LSP BFDs that are sent all along the MPLS connection. And by the same mechanism, A will, within 10 milliseconds plus the time to get plus some propagation and transmission time, will detect that the B is not responding to its BFDs, to its pings, if you want. When that happens, A will switch the traffic from the green to the red. So the time to detection will be typically much less than 50 milliseconds, but typically also more than 10 milliseconds. And after this short interruption, traffic will flow on the other path. This is the MPLS fast reroute. In extreme cases, you could do more. If you want to have the kind of reliability that we said before for applications that require few milliseconds of delay, you do what is called 1+1 protection, meaning that you duplicate all the packets that you sent over the two paths. You can do that with MPLS. If you do this with MPLS, that means the two packets, it will not be fast reroute, it would be 1+1 protection. The two packets are sent on both here. Of course, you have a problem when you do that. You need to remove the duplicates. Either the application is able to do it, but typically this is not the case. So if you do this, you need a mechanism to remove the duplicates. This mechanism is called PRP or IPRP. PRP, Parallel Redundancy Protocol, is a mechanism that allows to remove duplicates that are sent over a duplicate network. PRP typically works by duplicating the Ethernet layer. So this is done, for example, in substations, electric substations. Many of them use PRP. I said that a substation typically uses local area network technology only, not routers. In fact, they use it primarily because such duplication technology exists in local area network. So when a device is connected to a Ethernet switch, in fact, it's connected to two Ethernet switches, and every packet that it sends is duplicated, it's sent on the two interfaces. On the receiver side, then the Ethernet card, which is a special Ethernet card, it's a PRP Ethernet card, will see at the source, sequence numbers will be inserted, then the sequence numbers will be used to remove the duplicates. You can do that at the Ethernet level. You can do that at the UDP level. If you do that at the UDP level, you have IPRP, where with IPRP, the idea is the same. If you connect a device through two networks, perhaps even three, so a wireless network, then you can send the same packet 3 times, and at the receiver, you need to remove them. It's fairly simple to do, but the trick is, of course, to do that in a way that's transparent to the application, so that in both cases, comes as middleware in the case of IPRP, as hardware in the case of PRP, such that an application like the PMU sends in fact data to only one PDC. It's the middleware that will take care of discovering the other it sends to only one PDC, but it sends to only one IP address of the PDC. Is the software that will take care of duplicating the packets and removing the duplicates or the triplicates at the destination. In the case of PRP, it's done in hardware. What's the net effect? If anything goes wrong, if a switch is broken, if a line is broken, if a connection is lost, then the repair is immediate. You don't need to wait until you detect the loss, and you don't need to repair it by rerouting. So it is sometimes called 0 millisecond failover. You repair the loss immediately because here 2 packets are received. If this is broken, you still have 1 packet received. Of course, this will not repair all losses. If you lose the 2 planes, the network A and the network B, then you have lost connectivity. So this is how things are done in smart grid. In the context of smart grid, there are many versions of MPLS. MPLS TE is the one that is used by telecom operators to interconnect multiple private networks. In the context of smart grid, it's called MPLS TP. MPLS, as I said, is very complex, although the ideas are very simple, but there are lots of 4-letter or more acronyms. But let me simply give a simple illustration of what it does. MPLS TP is a technology based on everything we've seen so far. TP means, if you want, it's a subset of all the MPLS capabilities. That includes the things I've described before, the MPLS header with the labels and the functions, plus how you use it to do what is called adaptation. One way to view MPLS is it's a mechanism to interconnect things that should normally not be interconnecting using IP. The normal way of interconnecting any two communicating devices is to use IP, to use IPv6 today, IPv4 in the past. IP was made for that. But there are things you cannot do in this way. For example, private IP networks. So that's an example where if you're running a smart grid, inside your substations and inside some other equipment, you will have, for example, cameras. You will have video cameras. You also have servers and some devices, and those are typically on a private network. They don't have public addresses. You don't want them to have public addresses because you don't want them to be discovered by hackers and attackers. So you use IP private addresses, but then how do you interconnect two private networks? We've seen various mechanisms. MPLS is one of the ways to do it. We have seen other things. We have seen you might have also the red clouds, which are things that operate at the MAC layer, and you may want to interconnect them without paying the price of migrating everything to IP. Then you use MPLS for that. You have even worse things. You have called PW, which PW stands for pseudo wire. What is that? Some technologies use physical wiring. For example, plain old style telephone. Old style telephone uses analog thing where you connect an analog telephone, receiver, and two ends of a telephone line. And you have that kind of things in industrial networks. You have sometimes telephone equipment to be able to call or actuate a ring, something of that kind here. So this was typically in the past connected through circuit switch network. Circuit switch network are the networks that were used to interconnect telephones. This has disappeared. There are probably some who exist here and there, but the telephone network in itself has been dismantled and replaced by everything over IP, because today the telephone companies, they replace all the they put all the telephony flows over IP using MPLS, for example. In this case, when we do that, we offer an interface which is exactly the interface that a wire expects. What is a wire expecting? Well, a wire is typically a physical communication mechanism at some small bit rate, 100 kilobit per second, even less, sometimes 1 megabit per second. So you have an interface with a jack of some kind that expects a coding system at 1 megabit per second. How can you transfer that over a network without having physical wires that we saw 20 or 30 years ago? Well, you can do what is called an adaptation. You sample the signal, you put a hardware adapter here that will sample all the received signal, put them into an MPLS packet, typically a short packet of perhaps 40, 50 bytes. Why short? Because you want the delay to be small, because on wires delays are extremely small. So you create a small packet with all the samples that you've collected. You send them to the other end of the world, and here you do the reverse operation. When you do that, of course, it is essential that you guarantee to this MPLS connection a rate of 1 megabit per second if your wire was operating at 1 megabit per second. You will do that with the mechanism we've seen last week. You will put a token bucket filter on the system here that is dimensioned such that it allows exactly 1 megabit per second to go here, and your MPLS backbone will do the calculation such that this connection will happen at exactly 1 megabit per second with a delay that can be bounded as well. On the receiver side, there's a little trick. When the packets come through the backbone here, Not all packets will have exactly the same delay, but if we use traffic engineering with the network calculus calculations we've seen last week, you will know a guaranteed delay bound, which will be typically small, perhaps 10 milliseconds. So you know that the delay bound or the variable part of the delay will be 10 milliseconds. This is called the delay jitter. Then we know that every packet will come at the other end with, for example, a delay between 50 and 60 milliseconds. Now you need to put the packets back into the wire. What is the difference between a wire and Ethernet? When you send data into the wire, you have to send exactly 1 megabit every second. In fact, at a smaller granularity, you need to send data at exactly the fixed rate of 1 megabit per second. If your packets arrive with variable delays, sometimes you might have 10 packets that come together, sometimes because some of the packets were later than others. So you cannot have a constant rate of 1 megabit per second on the output if the delay is variable. The delay is variable because you have a packet switch network. What can you do? Well, you do what is called a playout buffer. You know a delay bound on the variable part of the delay of 10 milliseconds. What do? When the first packet arrives, you delay it by 10 milliseconds. You know that by doing that, any other packet will be on time, will never be delayed more than the delay you've imposed to that. So you can play those packets back at a constant rate and serve exactly a fixed number of packets every time slot, thus creating exactly the pseudo-wire behavior. So pseudo-wire is one of those legacy things. Legacy means things we do because we have old stuff to support. We would never do that if we would invent everything today. But because we have to interconnect a number of devices that are connected to wires, we do that. And we do that typically over an MPLS backbone. Voila, that's what MPLS is and why it is used. Here is a first little quiz. I let you discover it, stop the video, and move forward to see the answer. Here is the answer. Both are correct. Both are correct. Two different LSPs, LSPs is MPLS connections, cannot have the same label on the same port of a router because the label is exactly here used to differentiate between different connections. So here 49 and 47 must have different labels. The combination port label uniquely identifies an LSP in a given router. This is correct here. If I'm on this link here, the combination of the fact that it is arriving on port C and label 49 uniquely identifies it. Here is another quiz that I'll let you discover. Pause and look at the answer. What is the answer? Well, the question is, how does router B, MPLS router B here in this example, know that the green things that come here should be put on Ethernet as IP packets, means with ether type equal IP. We care about that. If we don't have the ether type, a packet cannot be decoded because when you read a packet, you see only zeros and ones. You don't only see bits. So you need first to know whether it's Ethernet. You know that because you are an Ethernet adapter. But then you need to know from the Ethernet header what comes next. So this you must do. But there is no Ethernet header inside the MPLS label switch thing other than the local Ethernet header if this is Ethernet between on this link, which is not always the case. But what will be used to know what is the type of the packet is the information that is stored in the MPLS table. So the nature of what is transported in an LSP is indicated when the LSP is set up, when the connection is built in the routers. In particular, it's not possible to mix with MPLS IPv4 and IPv4, for example, or traffic that is for interconnection of VLANs or IP connections. But that's Natural, the idea of MPLS is to use a network to interconnect things that are very different in nature over the same network. So this is why things are done in this way. Voila, that's the end of this session. I hope you enjoyed it.